In our previous video, we saw how a closed loop buck converter basically works. Here we are going to see how to design a controller for such a buck converter. First, we will be designing the controller in continuous time domain, and then in the further videos, we'll be exploring how to convert that continuous time domain into a discrete time domain and feed it inside a digital controller such as Arduino to implement it in the real world. As a first step, we need to first understand the nature of the system we are trying to control. The nature of the system here, which we are trying to control, which is a plant, is a non-linear time variant system. First, we need to understand what this terminology basically means. This could be split into two. One is non-linear and other is time variant. When we say a system is non-linear, here the system is non-linear because the components involved in forming the system are fundamentally non-linear components. How? A diode, if you take, for example, is a non-linear device. The IV characteristics of a diode is not a linear relation. It's a non-linear curve. Similarly, when you take a MOSFET, it also has a non-linear characteristics. So we are basically dealing with components which are non-linear, which are together put to form a system. Therefore, the system is also non-linear in nature. Coming to the second terminology, time variant. What do you mean by a time variant system at the most fundamental level? If I am having a system, for example, this is my system. If I am giving the same input to the system and if I am observing different outputs at different points in time, then we say the system to be time variant. Note the point that I am not changing my input here. My input is constant. In spite of my input being constant, there is something that's happening inside the system, as a result of which my output varies with respect to time. We call such a system as a time variant system. Now the buck converter or any power converter for that matter, when we talk about power converters, they are inherently non-linear time variant systems. So let us first understand why it is like that. For that, I would simply demonstrate a simple explanation. I will give you a simple explanation which proves that point. So this is my system. Basically, I'm going to give an input to the system. In our case, this is 24 volt. And I'm going to take an output from the system. Let us assume that the output is simply resistive for now. In real time, we do not model as a simple resistor. We model it as a current source or some other things. So we take such a system. When we observe the output voltage of the system, due to this switching action, the output voltage which you will get will be having a nature which will be very similar to something like this. This is your output voltage, this is your time axis. Whenever your switch is on, output voltage will rise. Whenever your switch is off, output voltage will fall down. For how much time it's rising and for how much time it's falling is basically dependent on your duty ratio. And again, it will rise, it will fall. You could see that my input here, in spite of being constant, because of the switching action, the switch is becoming on and off, and the switch is a part of the system here. Now we could evidently see that my output voltage is varying with respect to time and it's not a constant. So this proves, or this explains, why my system is a time variant system. Now the challenge comes here. When we want to design a controller, we usually go for transfer function, which is the most accepted and reliable way. There are multiple ways to control systems, basically control your plants. But we are going to see an approach which involves transfer function of different controllers, basically integral controller or proportional integral controller or a PID controller for that case. So these controllers are going to be designed using transfer functions. And when we talk about transfer functions, we talk about LTS systems. So let me explain that in detail. Our plant here is a nonlinear time variant plant, and our controller is going to be an I controller or a PI controller or a PID controller. If it is an I controller, then my transfer function will look something like this. It will look like Ki upon S. If it is a PI controller, it will look like Kp plus Ki upon S. If it is a PID controller, then it will look like Kp plus Ki by S plus S into Kd, something like this. Now, if I want to design my controller in these formats, obviously it is implied that my controller is in LTI domain. Means my controller is a linear time invariant system. That's why I'm able to represent them using these kind of transfer functions. If you remember the definition of a transfer function, you will come to know that transfer functions can be obtained only for linear time invariant systems. However, my plant right now is a non-linear time variant system. So what we do first is we convert this non-linear time variant system, non-linear time variant plant, into a plant who is linear time invariant in nature. How do we do this? By using some approximations. We do this, and at the end of the day, we obtain, this is nothing but we obtain a transfer function. We typically call that transfer function as del V naught of S by del D of S, which will be a transfer function, which will be something into S plus something upon S square plus something into S plus something. It will be like this. So this at the end of the day is going to be your transfer function. Now this transfer function represents my plant. I am willing to control this by another transfer function, which may be Ki by S. Now this plant is modeled in a linear time invariant domain, and my controller could be obtained by tuning this plant. So the idea here is to tune this controller. When I mean to say the word tune, I mean to say finding the optimum value of your integral gain, which is K here. When we want to do that, we want this plant to be represented as a transfer function, because in the next section we'll be seeing how to obtain this value using MATLAB. Now if you have MATLAB, you can do this by auto tuning. So I will be explaining how to utilize MATLAB to do the auto tuning here. I have put some snaps from the tool to explain how it will basically work. And I would like to tell one important point here. How to obtain this transfer function from this circuit is not covered under this course or series of videos. That's an entirely different topic. You may find some materials or papers on the internet to learn that process of converting a circuit into a transfer function. There are well-established ways for that. We usually call that as state space modeling. We use that method to obtain this. So I'm not covering that procedure inside this topic, as this series of videos is mainly focused on implementing the controller in Arduino. So now let us move to the section of how to get a Ka value for this particular plant. Now I have converted my plant into a transfer function using those approximations and using state space modeling method, and I have made a setup like this. So in MATLAB, you could see that this block is actually called as transfer function. It's called transfer FCN. This is the name of the block. If you search in the library browser, you'll get it. You can enter this del V naught of S by del D of S transfer function there. And you could see this is the controller. This is the integral controller. This actual name of the block will be PID of S. Here it is an integral controller because after tuning, I got to know that it is an integral controller. Anyway, I'll be explaining the process too, so please wait patiently. So the block name is PID of S, PID controller block. Now this represents our whole system. Now this represents the plant, this represents the controller. We are taking a feedback from the output of the plant. We are comparing the reference value with that voltage, producing an error. So this error is given as input to the controller, which will in turn give me the duty ratio as the output. And this plant is nothing but your representation of del V naught of S by del D of S. Now we will clearly understand why this transfer function is the one which we require. Because when you are doing voltage mode control, this is voltage mode control. When you are doing voltage mode control, the output of the plant is a voltage and the input to the plant is duty ratio. We know that transfer function is always the Laplace transform of output by Laplace transform of input. Now output upon input will give you this sort of transfer function. So this is how the signals and the blocks inside of this system will look like. I am just taking the output to monitor the output voltage here. Now we don't know what will be here. We don't know whether this is Ki by S or this is Kp plus Ki by S or this is Kp plus Ki by S plus Kd into S. We don't know what is this. So the intent here is to find out what is this and find out the values of Kp, Ki, Kd. That's the intention here. So we double click on this block. If you double click on this integral controller block, you will get a window like this. Initially, it may have some other value or it may have 0. All you have to do is check whether this is in continuous domain. This could be anything because when you auto tune it, it will give you by itself, and form should be parallel, and you have to click this tune button, and please ensure that transfer function based tuning is selected here. By default this will be the thing, so we have to tune it. The moment you click the tune button, you will have something like this. The dotted line here is the block response, which is already present, and the bold line here is a tuned response, which is a desired one which you want. Assume that you have a time domain specification, control system specification saying my settling time should be less than this much of millisecond. That is a domain. If that is a requirement, then you will make sure that that requirement is satisfied here. If my requirement states that my settling time should be less than 50 milliseconds, then it is satisfied here because it is only 15 milliseconds. Now, similarly, you may have another requirement stating that the maximum peak overshoot should not exceed 120% of the steady state value. You could see this is a step response basically. This is a step response, meaning whatever block I am having here, I am giving a unit step input to this, and I am observing what is its output. That output looks something like this. That is this output. Now, this dotted is the block, this bold is the tuned response. So I will also check whether my maximum peak overshoot lies within the range. It is lying within the range here because it is lesser than 120%. This is 120%. Is lesser than 120%. So my specifications are satisfied. Similarly, you may have some time domain specifications for your power converter. So how to tune this? I mean, how to get your desired response is by moving this slider and this slider left and right. You can experiment it, move it left and right, and obtain the desired response as you want. Now this is my desired response. The moment you observe this desired response, click on to this button called show parameters. Then a pop-up like this will open. Here it will say that the block had some value. It may be 0 or some other value. It had this value, but I have tuned it, and this is your desired value. So it is saying proportional is not required for your application. It is saying derivative is not required for your application. Only integral is required, and you have to put the integral value of 58.74 something. So this means it is indirectly telling me my controller transfer function, which is k by s, should be actually equal to 58.7485 upon s. So my k value is 58.745. Right. So this is the thing that we will get. So now I got a k value. If your system demanded a proportional integral controller, if your plant demanded a proportional integral controller, then you may have some p value here as well. So once you get that, click on to this button, update block. So these parameters will be directly updated to your block, and it will directly be reflected here again. Now you click OK, and then you can run the simulation. Once you run the simulation, you will get the same output as I showed you in the earlier stage. Here I have to get 12, I'm getting 11.97. If we attach a scope here and see the waveform will be a transient which will settle around 12 volt. This is the way in which you have to find Kp, Ka, Kd value for your power converter.